So after that last video, the first video that we saw, I want to kind of summarize what it is that you need to know about solving problems for the exam itself. Because that last video, the whole point of the last video was to show you how to go from graphs like this to equations. So we went from graphs to equations like x equals 1 half at squared plus v naught t plus x naught, and v equals at plus v naught, and v squared equals v naught squared plus 2a delta x. So the whole point of the last video is you have graphs. How do they connect with equations? How are those two things connected? And the thing about the exam is if you sit there and say, I can do graphs and I can do equations, and I have no idea how the heck those two things relate to one another, you can still get an A in the class. And that sounds like a really cynical thing to say as a teacher, but the truth is sometimes you have to wait for your second or third physics class to see the really deep connection. So if you can do graphs and you can do equations, you're going to do fine. So what I wanted to do, just to kind of help both sets of people, those who understand the connection between graphs and equations and those who don't, is solve one problem. But we're going to use both approaches. So what this does is it says, here's a problem. How do I attack it every single way? So the goal at the end of this is you will see how to solve one problem using every single approach that you are responsible for the exam. So we're going to do this problem first using the graphical approach. So here we go. We have a car that goes from 0 to 60 miles an hour in 7 seconds. And since this is clearly an acceleration problem in this first one here, we can tell that, we know that we can use our RampLab equation. And the RampLab equation says v equals at plus v naught. So now what we want to do is go into this problem and figure out what each one of these letters is. So when we look, we say that, okay, this is 0, that's the initial speed, the initial velocity, sorry. We have the final velocity as 60 miles an hour. And since we're working in meters, what I want to do is actually do a unit conversion for you. So let's use bubble method for that. So we're going to take 60 times 1610 meters over 1 mile. And then we're going to convert hours to minutes. So we have 1 hour, sorry, not to minutes, but to seconds, 3,600 seconds. And so when we convert this, we're actually going to get v final equals 26.8 meters per second. So that's the number that we're going to use. And then we have 7 seconds here, which is the time. So now it says calculate the car's acceleration in meters per second. So we have v equals at plus v naught using the RampLab equation. And so for v, we have 26.8. We have a is the unknown, t is 7 seconds, and v naught is 0. So then we can actually go ahead and get our acceleration. And when we do that, we divide both sides by 7, and we'll actually end up getting 3.83 meters per second squared. So now, if we're using the graphical approach to solve, here's what we do. We take the general RampLab equation, v equals at plus v naught, and we plug in the acceleration, so v equals 3.83t, so we've got the slope there. And the intercept, which is the velocity, the initial velocity is 0, so that's plus 0. So we're actually left with the equation v equals 3.83 times t. So now we're going to go ahead and we're going to graph that like this. So what happens? We look at our graph and we realize we go from, in 7 seconds, we go from 0 to 26.8 meters per second. So that's v versus t. And this happens at 7 seconds, so right here, 26.8. And then we drop a dashed line here and we say, okay, the height of my triangle is 26.8. The width is 7. And so to get the area of this triangle, to get the displacement, delta x equals the area, because we want to know how far it went. That's going to be 1/2 times base, which is 7, times height, which is 26.8. So we end up getting, when we do this math, it's going to be, I'll just do the math here. You can do this in your calculator. So we end up getting 93.8 meters. If I do this right, some of you get like 93.6, some of you get like 94. That's fine. We're close to the answer. 93.8 is the answer that we get. So that's how we actually do this problem using the graphical approach. This is one thing that you need to know how to do for your exam. So this is like one big outcome for your exam. So you need to know how to do this. And I did videos last week in week 5, so this is actually, I should say, week 6 lecture too, and I apologize for getting the week wrong in the last video. This is one big thing. There's lots of examples, so you need to get fluent in this by practicing again and again and again. Okay, so that's one approach. Now, it says plot the position, velocity, and acceleration. If we were to actually do that and do qualitative graphs, let me actually just kind of set those up really quickly. And this is going to be identical for both videos, so for both ways of doing the problem. So I'm actually not going to repeat it. What I'll show you is if you were to plot those, what you'd get is position versus time, velocity versus time, and acceleration versus time. And we'd get like an equation like this, or a graph like this. For velocity, it would be like that, and for acceleration, it would be like this. So there you go. Okay, so that's one problem solved one way. Okay, and there's the graphs. So now we're going to do the same problem, and we're going to be using the equations approach. And I actually have an approach that is designed, it's in Learning Packet 5, and there's a handout that says way to solve equations, or like approach to solving equations, and you're expected to follow that. So we have 3 equations in the handouts in Learning Packet 5. And again, this is week 6, lecture 2. We have x equals 1/2 at squared plus v naught t plus x naught, which you actually saw where this came from in video 1 of this week. So lecture 1 explains why this works. This is true. Why it's true. But we don't really care. If you want to be kind of cynical and just think, okay, what do I need to know for the exam? You need to memorize the equation. And then we have v equals at plus v naught, and that's it. Okay. So now what we're going to do is, so we have the equations, so we do exactly what we did in the last part, which is we read the problem and label every variable. So this is t, and then this will be v final, which on the last page we converted to 26.8 meters per second. So I'll say see previous page, okay, which you should also have in your notes. And this, of course, is v initial. And we want to know how far we want to know what the car's acceleration was and how far it was going. So now, I'm going to do this problem with a little bit of overkill. We have an idea that we should use this equation from the last page, but I want to show you what to do in general when you have a new problem that you're doing on your exam. So I'm just going to tell you right now, I'm going to overkill. Let's overkill. That means we will plug every number into every equation like this. So we have x equals 1/2 at squared plus v naught t plus x naught. So we plug in the numbers that we have. We don't know x, we don't know a, equals 1/2 a times 7 squared plus 0 times 7 plus 0. Okay. Again, that hint that I gave you in class last time, if they don't give you, so if they don't tell you or ask you to solve for it, assume x naught is 0. So we're going to do that right here. So this equation, it's 2 letters missing, so we just put this aside and try our next equation. So let's do it. Our next equation says v squared, so that's 26.8 squared equals 0 squared plus 2 times a times x minus 0. We don't know x final, we don't know a. So we're going to put this equation aside as well. So now let's use our last equation. So we have v equals at plus v naught. So what I did here is, sorry, I should have been a little bit more clear. What I was using was I was taking this equation here and putting in the numbers right here. So sorry I didn't write that down. Now, for the third equation, let's go ahead and plug in our numbers. So we're actually going to have 26.8 equals a times 7 plus 0. So a is the unknown. And we can actually do our algebra, and we will get that a equals 3.83 meters per second squared. Okay. So now let's go ahead and do part 2, where we want to find how far it goes when it was accelerating. So now we have two equations that have x. Now before we had two unknowns. We had x unknown and a unknown. A unknown, x unknown in both of these. But now if you look, we realize, wait a second, we just solved for a right here. And now what we can do is we can take that and plug it into, say, this equation or this equation. I'm going to go ahead and plug it into this equation right here. So we will get x equals 1/2, and now I put in what I just solved, times 3.83 times 7 squared plus 0 plus 0. When I go ahead and do that, I'm going to get 49 times 3.83. So I'll go ahead and calculate that number. And when I get that answer, I'm going to end up getting 93.8 meters. So that is, just to kind of compare with this page, that is another big outcome for the exam. And by the way, in a sense, we can kind of say the third big outcome is if I told you that the position graph of this object looks like this, you should be able to, on this position graph alone, be able to tell me, by looking at this position graph, that the velocity graph for this should look like this, and the acceleration should look like this. So being able to predict, so going from here to, predict this graph, or predict that it should look like this, or just be able to tell that it looks like this, and same here. Okay, or deduce or predict, whatever word you want to use. If you know this graph, tell me what this is, and tell me what that is. That's like your third big outcome. So far, those are like the three big things that you should know how to do for the exam so far.